downstairs.
Yeah, it's really neat. There's two other damagers to here. One for video, one for gaming.
Hi everyone, we are at Danbury. First of all, we would like to thank Sikorsky and Connecticut Corsair for giving us this opportunity that has really helped to shape many of the majors that we want to pursue in our higher education. We would also like to thank the judges who have taken this time out of their Saturday to come listen to us present.
Our task is to improve the original design of the F4U Corsair's drag braces. We need to make them lighter and more cost-effective than their predecessors. We came up with 4 solutions so that we can control the weight and cost of each part individually, making them a lot cheaper and a lot lighter.
So for our engineering process, we got to be able to understand the problem given to us. So our problem was we had to redesign the drag link for the F4U Corsair. We had to do background research, which would help us further understand what the drag link did itself, and then what we could do to make it better. Our plan incorporated all of our team members here that worked to complete the process. We had a brainstorm, evaluate, and choose a solution for the drag link itself. And we had to be sure our solution met the requirements given to us by Sikorsky and Connecticut Innovations. We developed a trade study and communicated our results through the final presentation.
So this is, for the most part, what we and the drag race are up against. We could demonstrate for you. Imagine for me that this right here is the barrier wire, and these are the landing gear assemblies on the F4U Corsair. When coming down the runway, if it missed the arresting wire on the aircraft carrier, it would hit these on just above the wheels, and it would cause a massive force into the, that's tangled. That's pretty much it. It would cause a massive force up into the drag braces here, a very strong force. There was also a lateral force that caused rotation around this way that would cause most of the force to be placed onto the inner drag brace, the part that's on the inside of the plane. Next slide. As you can see here on how we depict that on the free body diagrams, the force was inversely proportional to the radius away from the center of rotation. Next slide. And when we took those two forces in the different directions, we could also consider them as a rotation around this axis here, which led us to a force on the inner drag brace upwards of 80,000 pounds during an extreme bear engagement. This is involving 6 Gs of force backwards in the direction towards the tail of the plane. That's it.
So our background research helped us understand what the drag links did. The main purpose of the drag link was that it kept the oleo strut and main landing gear from folding back up onto the wing in an extreme landing environment. It was also used in carrier operations where when the planes landed in a recovery, they were pushed towards the end of the deck. And if another plane were to miss the approach, it would careen into the other planes. So there was a barrier wire, as shown in the demonstration there, that caught the oleo strut and prevented the plane from careening into the other aircraft. And the drag legs itself kept the oleo strut from completely collapsing back and resulting in a total loss of the plane.
Here in Danbury, we like to make colorful charts. So this is our project plan chart. We started off by with the history, which involves what the landing gear is, why it failed, and how we can possibly fix the problem. Then we moved to free body diagrams to identify what forces were actually affecting the landing gear, and we found how detrimental the impact of that force was. A big chunk of our solution came from understanding the Johnson-Euler buckling formula. It had a very hard component to it, which involves kind of looking at the density. We moved on to the trade-off matrix to decide what is our ideal new design, and we had to evaluate the plane on ground and air for our shapes, I-beam and cross-beam, our materials, steel and aluminum, and for the lower and upper member.
In connection with any problem we had to face and try and figure out what the risk would be at hand, and also that would accompany us and perhaps hinder us from completing the project. So on the right we have, on the top right, one of our critical risks was with the material aluminum. And with the materials that we were provided, we found out that aluminum was more susceptible to corrosion, and that was very influential in us disregarding aluminum and focusing more on steel. And also, one of the marginal risks was determining whether we would be off schedule. So here we have a chart that pretty much divides all of the objectives and all the aspects of this final project, and we have all of our members indicated, and also the time that it took to work and the specific roles and responsibilities that they had.
For the requirements given to us by the challenge, for the cross-sectional area, we had two potential envelopes, both the ideal and the acceptable envelopes. We considered both in our calculations, but decided in the final process to only consider the ideal envelope, as if we expanded into the acceptable one, it might cause additional issues with the functioning of the plane that we are unable to take into account through our design and our knowledge of the process. For the actual shape of our design, we considered multiple different options. We considered a hollow tube, a rod, a crossbeam, as well as an I-beam. Upon consultation with our mentor, we decided that the hollow tube would leave open spaces and that corrosion might occur within the tube that we would be unable to see if we were going to do repairs, and that would be a detriment to the design. So we decided to go only with the cross. We decided to compare both the cross and the I-beam in order to assure that there were no potential inside spaces unseeable for corrosion. We considered both air support and ground support separately, as well as the upper and lower member of the drag race. Additionally, we considered the I-beam and the crossbeam, as well as aluminum and steel for materials. The air supremacy design has to be primarily light so that the aircraft is more maneuverable, whereas the ground support needs to be less expensive as the design can compensate with a heavier mass.
Okay, the next part of our engineering process was the Johnson-Euler formula. And when we were looking at the Johnson-Euler formula, as we will later explain, we used a program. And the main component that we were changing within the program was rho, a little P-looking thing. And the only thing within that formula that would be changing as we were looking at the different members and the different masses, well, within the different materials, was I and A, and I is the moment of inertia, and A is the cross-sectional area. So all other components of the Johnson-Euler formula remained constant. And what it allowed us to do was calculate the buckling force that each member could handle, and we used that in our margin of safety. We calculated at the beginning of the project what the
told what the force was going to be on each member, and then we saw with the Johnson-Euler formula what each member could handle given our changes of I and A, and that would change with our designs, the cross beam and the I beam. They had to handle both forces on the X and Y axis. So they needed to be able to be symmetrical, which both could handle. And yeah.
So this is a depiction of the program that we were talking about. We're going to see a video of that running through right now. The video? Oh, that is. As you can see here, there was only two variables that we ended up changing. It involved the thickness of the webbing of the I-beam and the thickness of the flanges. It incremented their values in increments of 1/100 of an inch and checked each combination of the thicknesses for strength and their weight. If it had sufficient strength and it was a lower mass than any previous designs it had checked already, then it would save that design as the optimal one. So after running through it, actually you can see that it will eventually, the mass will stop incrementing. It might have already reached its optimal design. And you can see a counter up there with all the calculations and the possible combinations that we checked through. And it takes a few minutes to do, but this is only for one combination on the lower member meant for air supremacy, which is a lower force and made of steel. We did 16 other combinations in columns like this, leading to calculations upwards of 250,000 in different combinations.
Okay, and when we got through all those calculations, we came up with solutions. We looked at the masses. We wanted to see the lowest mass so that we could take into effect the weight of each of them. We wanted the minimum amount of weight, and we wanted the minimum amount of cost, and that's what came into effect when we were looking at the mass. We had ideal and we had exceed for the envelopes that we could put these designs within. And you'll see up there's NA. Those were designs and materials that couldn't handle the ideal situation, so they would have to be the masses in the exceeding envelope.
From these numbers, we decided to take them. We decided to make an Excel chart that decided the cost and for each dimension. From here you can see that we found from the chart that in the Excel document we found the total cost out of the materials, stamping dies, maintenance, and manufacturing cost, and we added it all together to get cost of 1 unit. And in this chart we compared all of the masses and the cost of 1 unit, and then we figured out the cost of 1,000 units.
Okay, for our trace study, we would basically, this is where we were deciding which solution would be our best. We did it a little bit differently. We had weighing scores. We weighed weight as the most important just for the air supremacy. For the ground supremacy, there would be other factors looking at where weight wouldn't be as important because the design could handle it. But for the air supremacy, we had weight as number 1, manufacturing cost as number 2, and then material cost as number 3. Then within each of the designs, the cross and the I-beam, and for each of the materials, we ranked them. So 1, 2, 3, or 4 for 4 options. In other options, you would only have 1 or 2 because the NAs where we wouldn't be able to put a design that would not fail within the envelope. And then we had the totals, and that would be, as you can see, the steel beam was our lowest score, and that was the score that we were going to look at. The green is the best, and that's what we decided to go with.
So as you can see, we successfully understood the problem in context.
We made a plan and we analyzed the requirements, and then we evaluated and chose solutions that would meet those requirements. After over 250,000 calculations in various trade studies and matrices, we concluded that these were the best solutions. You should pick our designs because they are the least expensive, they are the lightest, and they are the most effective for the Corsair. Thank you for your time.
If any of you would like to see this model, I could hand it over to you. We also have the I-beam that is our exact solution. It's a modified I-beam, not the original one. We modified it to specific dimensions, and if you guys would want to see this. Anybody? And questions?
Excellent presentation. You noted in one of your slides that you did 250,000 calculations on the spreadsheet. What if you made a mistake in the program? How programming becomes rather complex. What were your approach to that?
We checked over the program a lot. That was something we probably spent a good deal of time on. We were sure there weren't any mistakes. We tried on different versions of the program to make sure they would run every same time. We ran the program multiple times to make sure it came to the same answer every single time, so we're sure that there weren't any errors. Anything else?
Yeah, there's great job. Thank you. There's quite a few of you. And how did you guys divide and conquer? Like, how did you guys arrive on who did what?
At the very beginning, when we were assigned this project, we had a couple of brainstorming meetings to figure out exactly what we wanted to do, what direction we wanted to head in. Our mentor was a great help in this, as was Mr. Parker. We designated tasks for everyone that was shown in our roles sheet right there. Every group member was made to they had to do their part. And then at the end, we brought it all together. We all talked about what we wanted to do, and then we made this PowerPoint right here. We then practiced this presentation, and we hope that you enjoyed it and got good information from it.
We also, throughout the entire process, we actually elected team leaders. So for the first module, we had a team leader that kind of oversaw the research report, and we went through every module with the team leader. And for this final project, we had 3 team leaders, and we all made sure that everybody was kind of doing their own part. We had a team leader kind of for every section that we had for the initial 4 projects. And so everybody was cracking down on each other to make sure that we could finish this for Sikorsky. Anything else?
So this is your final design, correct? So out of all the 16 pieces, winner. Very good presentation.
We have 4 finals, so like 1 upper, 1 lower for like ground and air.
It actually, when we were comparing the cross-beam and the I-beam, it turned out that the redesigned I-beam came out as the best solution with the best mass and the best margin of safety. Up on the screen, the B, D, H, T, and S, those are all components, the different components within the I-beam that tell you the dimensions of it. So we found that is I guess that would be one of our solutions.
So at the end of the day, how many I-beams solutions are there? You got me confused.
There are 4 solutions. We decided to try and find the best solution for each situation because the airplanes, as you said in a previous presentation, you were concerned about having to switch out parts. Our parts are designed so that you can put them in, take them out. It's very easy to do. In addition to that, the ground support design will work for air superiority as well. So that one is good for both. We just did the air superiority one in addition to that because it is lighter and it would be more effective in an air fight.
So the air support works in a ground support situation?
Ground support works
works in an air support situation because it's stronger. And then we have the lighter version, which is a little bit weaker for air superiority, so that it has more maneuverability.
Only the air support.
Yeah.
Thank you.
Thank you.
Just one more for me. Did you guys have fun doing this?
We had a lot of fun.
Okay, good.